Hello everyone. In this lecture we will discuss some problems related with magnetostatics. So first problem here is a long copper rod of radius r carries a uniformly distributed current I. Here we have free current. Find H, that is auxiliary field, inside and outside the rod. So as per our problem, suppose this is a copper rod and here this is the radius of the copper rod, and suppose the current I flow in the upward direction, and here suppose this is a Amperian loop having radius s. So this is a Amperian loop. Okay. Now to understand this, we will draw a laboratory picture. According to this is a copper rod and this is a laboratory picture. So as per problem, suppose current I flow in the upward direction. Because copper is a diamagnetic material, so volume current or volume bound current will move in the opposite direction. So it means if we have rectangular loops, then the current flow in this direction like this, downward, upward. That is, here the volume bound current will flow in the opposite direction to as that of current I, and direction of the surface current is same as that of current. So here the direction of the surface current is same as that of I, and the volume current or volume bound current is opposite to that of I. Further, here it means this is the direction of H, auxiliary field, and this is the direction of M, that is magnetization. Because again copper is a diamagnetic material, so the direction of magnetization is opposite to that of auxiliary field. So this is related to the direction. Next, so as per Ampere's law, we know H dot di line integral is equal to free current enclosed in the Amperian loop. So here for inside the rod, that is when S, that is radius of Amperian loop, is less than capital R, that is radius of the rod, then we can write above equation, that is h. When we integrate di, we get 2 pi s, that is circumference, and here in this case I is we multiply, I is the current given by as per problem, and here we have a ratio of pi s square over pi r square. Okay, then h is equal to I dot ps square over pi r square and into 1 over 2 pi s. So this pi is cancelled with this pi and s is cancelled with this, so we get h is equal to I over 2 pi r square into s. Because h, that is auxiliary field, is a vector quantity, so we can write h vector equals to I over 2 pi r square s, and here we have phi cap. So this is the auxiliary field inside the rod. Now for outside the rod, that is s greater than equals to r, we can write h. Again we have a circumference of Amperian loop, that is 2 pi s, and this is equal to I. So here h equals to I over 2 pi s. So because this is a vector quantity, so we can write h vector is equal to I over 2 pi s, and here we have pi cap. Okay, so auxiliary field for inside the rod, this is equals to I over 2 pi r square s phi cap, and for outside the rod is equals to I over 2 pi s phi cap. Okay, then we have a second problem. In second problem is an infinite solenoid. In solenoid we have n turns per unit length and having current is I. This solenoid is filled with linear materials of susceptibility chi m. Find the magnetic field inside the solenoid. So here we are interested to find the magnetic field, that is B. So as per our problem, here suppose this is a infinite solenoid, and suppose here this is a z cap, that is the direction of magnetic field, and these are the number of turns, that is n turns per unit length, and suppose this is the direction, here this is phi. So again here we apply the Ampere's law for auxiliary field, that is h into di line integral, this is equal to I f free charge enclosed. So here finally h is equal to n I z cap. So here n is the number of turns, I is the current, and z is the direction. But we know that this B, that is magnetic field, equal to mu naught 1 plus chi m, and this is h vector. So here because h is equals to ni z cap, so we can write mu naught 1 plus chi m, and here we have ni z cap. So this is the magnetic field for the solenoid. So here B equals to mu naught 1 plus chi m ni z cap. So here magnetic field, it depends upon the magnetic susceptibility. So for paramagnetic material, value of magnetic field is slightly enhanced, and for the diamagnetic material, because it's a negative value, so magnetic field is slightly reduced. Further, we have a bound surface current. So in case of bound surface current, so we know basic formula, that is KB equals to m cross n cap. So m we can write like this, that is chi m h cross n cap. So why it is so? Because magnetic susceptibility is equals to m by h. So here we will put the value of h, that is chi m, and here we h value is equals to ni. So finally here for the bound surface current, direction is phi cap. So KB is equal to this value, that is phi m ni phi cap. Next important point here is direction. So here direction of bound surface current is same as I for magnetic susceptibility greater than equals to 0. So direction of the surface current, surface bound current, and the direction of current is same, that is they are parallel for magnetic susceptibility, for the materials having magnetic susceptibility is greater than 0, that is if we have a paramagnetic materials. And direction of magnetic susceptibility, KB, that is a bound surface current, is opposite to I, that is direction of current for the material having susceptibility is less than 0. That is the direction of current and bound surface current is same for the paramagnetic material, and this is opposite for the diamagnetic materials. Or mathematically we can write for materials having magnetic susceptibility is greater than equals to greater than 0. In that case, bound current and the current is same in the same direction, and when the material having magnetic susceptibility chi m is less than 0, in those materials direction of bound current and the current is opposite. Okay, thank you.